Section 3.2, solving linear programming problems graphically. Many real-life problems involve a process called optimization, which means finding the maximum or minimum value of some quantity. Linear programming is the process of optimizing a linear objective function, subject to a system of linear inequalities called constraints. The graph of the system of constraints is called the feasible region, so the part that is highlighted. The following graphs show regions of feasible solutions. Use the regions to find the maximum and minimum values of the given objective functions. So the objective function is z equals 3x plus 2y. And I have 4 points that we have to check each one with to see which will give the minimum and which one will give the maximum. So let's just start at 0, 0. So if I plug 0 in for x and 0 in for y, what result will happen? So 3 times 0 plus 2 times 0 will give me 0. And we'll just go clockwise around. So let's do 0, 40. So what happens if I plug 0 in for x and 40 in for y? We will get 80. And then continue on. So 3 times 30 plus 2 times 30. Let's see here, that's 90 plus 60 is 150. And then finally, 3 times 40 plus 2 times 0 gives me 120. So the corner point, that should be a 0. I don't want to put a 2. So the corner point 0, 0 gave me my minimum value. And my point 30, 30 here gave me my maximum value. Okay, let's try with the objective function z equals x plus 4y. So we're going to do the same thing. Let's replace x with 0 and y with 0, and we will get 0. Let's do 0 plus 4 times 40 would give us 160. Let's do 30 plus 4 times 30, so 150. And 40 plus 4 times 0 would give us simply 40. So again, the point 0, 0 is our minimum value. And the point this time also is 0, 40 here. This point here also resulted in our maximum value. Alright, let's give a try finding our maximum and our minimum value here. We have, let's see here, we've got 3 points that we need to consider. And we have an objective function 4x plus 2y, so we'll plug in. We'll start at the top left there, so 4 times 1 plus 2 times 4. That's 4 plus 8. 12. We'll move on to the point 2, 1, so 4 times 2 plus 2 times 1. 8 plus 2 is 10. And we have the point 4, 0, so 4 times 4 plus 2 times 0, that would be 16. We technically don't really have a maximum because, as you can see, our graph continually goes this direction. So we don't have any max. We have no max. Even though I see there is a 16, but it could be more, but there's no ending, so it just keeps moving this direction. So it's going to keep getting larger and larger. No max because graph extends upward. but we do have a minimum. Our minimum value is at this point here. All right, so let's try with the optimization at 4x plus 7y. So we'll just continue 4 times 1, 32. 4 times 2 plus 7 times 1. 15. 4 times 4 plus 7 times 0, 16. So again, we have a minimum. But like before, since our graph keeps extending upward, we're going to have no maximum. Because the graph extends upward. Let's use graphical methods to solve the linear programming problem. So we want to minimize. So we want the smallest number possible. And our optimization function is 4x plus 7y. And we have some constraints here. We have to graph these constraints. Looking at x is greater than or equal to 0 and y is greater than or equal to 0. This just means that we want to be in quadrant 1. So as I'm graphing, I only care about things that are happening in quadrant 1. Because we want x to be greater than 0 and y to be greater than 0. So we want all positive numbers. But we do have to do a little bit of side work here. We'll come back to the x minus y. So 3x plus 2y is greater than or equal to 18. 2y is greater than or equal to negative 3x plus 18. Divide by 2. Y is greater than or equal to negative 3/2 x plus 9. So we have to graph this one. And we also have to graph x minus y is greater than or equal to 1. So negative y is greater than or equal to negative x plus 1. Here we're dividing by negative 1, so we have to reverse our symbol. So y is less than or equal to x minus 1. So let's graph these. We have to graph this one and the other starred one. So we're going to go up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Up here. And we have to go down 3 to the right 2. And we have a solid line. And we want to shade above this line. So just keep that in mind. We want to shade above this line. And we also have negative 1. And we want to go up 1 over 1. And this is also a solid line. And we want to shade below here. So we want to shade above this line, but below this line. So the part at which is all shaded is this area here. So we want to find the minimum point, and we have some points at which it hits, because it's going to hit. Here is a point we need to check. Here is a point we need to check to see which one will result in the minimum. So we need to check the point 6, 0. Hopefully on your graph you can see it a little better than my graph. And then we also need to check the point 3, 4. Again, I didn't graph very well, but we need to check these 2 points to see which one works the best. Oh, I'm sorry, not 3, 4. We need to check 4, 3. Over 4, up 3. There, that looks a little better. And we need to determine which one, using our formula here, which one gives us the minimum point. So 4 times 6 plus 7 times 0 would give us 24. 4 times 4 plus 7 times 3 would be 16 plus 21. Well, that's already above, so it would be 37. So the minimum point, so our minimum of 24 at the point 6, 0. Let's use graphical methods to solve the linear programming problem. We want to maximize, so we want to maximize, find the largest number when we have the optimal function z equals 5x plus 2y, and we have some things that we need to graph. We're going to have some bigger numbers here, so I'm going to let each one of these equal 2. So I'm going to scale by 2. Alright, so first we need to solve for y here. We have 4x minus y is less than or equal to 16. So negative y is less than or equal to negative 4x plus 16. Dividing by negative 1. Since we're dividing by negative 1, we have to flip our sign. So to graph, we're going to start at negative 16. Keeping in mind we're going by 2's. 14, 16. And we're going to go up 4 to the right 1. Oops, we should have been in the middle. There we go. And we are going to have a solid line. Alright, we have 2x plus y. It's greater than or equal to 11. So y is greater than or equal to negative 2x plus 11. So we'll start at positive 11. So we go up 11, we're going to be in the middle. And we have to go down 2 to the right 1, so we're going to be in the middle again. And we're going to have another solid line. And keep in mind we want to be above this line and above the other line. So kind of in between the two is where we're going to be. Now we have some constraints. We have to have x greater than or equal to negative 3. Excuse me, x is greater than or equal to 3. So we need to find 2, 3. So x has to be greater than this line, so we're going to be to the right of this line. And at the same time, y has to be less than or equal to 8. So we have to be below this line. So the part that's shaded, considering all of those elements, is in this area here. And we have the points. I've got some fat lines there, so I'm going to give you the points at which we're going to have to check. And these should match if you're working on your paper in front of you. You should be able to see these a little nicer. We have to check the point 6, 8. We have to check this point here, which is 4.5, 2. We have to check this corner point here. And this corner point is 3, 5. And then we have to check this corner here, which is 3, 8. And we want to find the maximum value using this equation here. So we'll just start with 3, 5. We'll start at this start here. So 5 times 3 plus 2 times 5, 15 plus 10 is 25. Then let's check let's go and check this next. So 5 times 4.5 plus 2 times 2. So we'll have 22.5 plus 4, which is 26.5. So we're already a little bit bigger than the last one we checked. Let's do the point 3, 8. So 5 times 3 plus 2 times 8, so 15 plus 16 gives me 31. So we're a little larger. And then let's try the last point, the top right corner point. So when you take 5 times 6 plus 2 times 8, so 30 plus 16 gives us 46. So our maximum is at 46. At the point 6, 8. Okay. And finally, let's try one more example. We want to maximize using this equation. We have some constraints. Our constraints, first of all, x is greater than or equal to 0, so we're just looking at quadrant 1. First of all, so we'll graph those points in. So we want to be in quadrant 1, so we want to be all positive numbers. So let's look at 2x minus 3y is less than or equal to 12. So negative 3y is less than or equal to negative 2x plus 12. If we divide by negative 3, we are dividing by negative, so we have to switch our sign. So we have to graph this one. X plus y is less than or equal to 5, so y is less than or equal to negative x plus 5, so we have to graph this one. And then we have to graph 3x plus 4y is greater than or equal to 24. So 4y is greater than or equal to negative 3x plus 24. Y is greater than or equal to negative 3/4 x plus 6. Again, we didn't have to change our sign because we divided by a positive number. So let's go ahead and graph all of these. Okay, so if we start at negative 4, we have to go up 2 to the right 3, up 2 to the right 3, something like this. And we want to shade above this line, so we're still in the first quadrant. Gotta go up 5 And go down 1 over 1. Another solid line. So this one we want to shade above. This one we want to shade below. So we're still in that triangular area. And then if we go to positive 6, 1, 2, 3, 4, 5, 6. This one says we want to go down 3, 1, 2, 3 to the right 4, 1, 2, 3, 4. Down 3 to the right 4. We have another solid line. But this says we want to shade above. Oh dear. Well, they're never going to overlap because this one is shaded above and everything else is in this area. But this constraint says that we have to shade up here. So there is no solution because there is no feasible area to check. And this concludes section 3.2, Solving Linear Programming Problems Graphically.